Hello and welcome to lesson number 2 in unit number 1, linear systems in our grade 10 academic math class. This lesson is investigating intersecting lines in linear systems. So last lesson we looked at how to graph straight lines on a coordinate plane, looking at 3 methods. If we now consider multiple straight lines on the same coordinate plane, there's really only 3 ways that they can interact. We're going to examine those on this first page of the lesson by doing some graphing. So the first thing we're going to do is graph the same line in all 3 grids, and that line is right here. We're going to graph 3x plus 2y equals 10. So in order to do that, I've rearranged it, so I'll just zoom in on that. I've put it into slope y-intercept form. I transposed 3x over to the other side of the equation. I have 2y equals negative 3x plus 10. I divide both sides, or all 3 terms, by 2. Leaving me with y equals negative 3 over 2 x plus 5. So y-intercept, rise, and run. So I put that on the graph already. There it is. I'll just zoom in. You can copy that out if you want, or just observe it in all its graphy glory, but there it is. It goes through 0, 5, goes down 3 over 2, put a dot, down 3 over 2, put a dot, etc. I've labeled both the y-intercept and the equation. The x-intercept doesn't go through an integer, so we've left it off. Now, first line's on there. One of the ways that two lines on a coordinate plane can interact is for there to be no solution at all. And when we talk about solution, what we mean is having a point of intersection, a place where these 2 lines touch. So one possibility is that the second line that we draw on this coordinate plane won't touch at all. How would that work? Well, let's have a look at the paragraph here. This is called an inconsistent system when that happens, and that's something you're going to want to remember. An inconsistent system has no solutions, which means there's no point of intersection. Now, if we think about it, what that means is that whatever the slope of our first line is, the second line that creates the inconsistent system, that creates a line that has no solutions with the first, it must have the same slope. They are going to be parallel lines, but they will have different y-intercepts. They'll have to go through a different place on the y-axis in order for it to be both parallel and not actually on top of it. So I've just written in an example of a second possible equation here. Y equals negative 3 over 2x minus 4. It could have been negative 3 over 2x minus 50 plus 2. Whatever it is, it just can't be plus 5 because that one's already taken. So we're creating parallel lines. Let's get this on the graph. So in order to do that, we have here our y-intercept and our rise, and our run. So let's get that on there. So we've started at minus 4. 1, 2, 3, 4. There we go. Oops, that's a highlighter. So there's, let me get a different color here. Here we are at minus 4. We go down 3, 1, 2, 3, and over 2. And down 3 and over 2, and we're going to keep that going the whole time. So up 3 over 2, up 3 over 2, and I'm going to try to draw a straight line through that without making too much of a mess of it. Oh, I wanted a straight line. Please and thanks. All right, there we go. See if we're hitting enough of these. Yeah, it looks pretty decent. Okay, that's parallel. Take my word for it. So we are going to label our y-intercept 0, negative 4. We're going to label our equation, which was the same as the other one, y equals negative 3 halves x, except a different y-intercept, minus 4. So what we've created here is an inconsistent system. There's no points of intersection for these 2 lines, and it's because they're parallel lines essentially. So that's one way 2 lines can interact. A second way is called a dependent system. And a dependent system has an infinite number of solutions. Now, what does that mean? It means that literally the line is on top of the other one. So they will have this same slope, but not only that, they will have the same y-intercept as well. So it's essentially just the exact same equation. It was y equals negative 3 over 2x plus 5. So there it is. That is the line that will create a dependent, or a system with an infinite number of solutions. Another way to do that, to sort of create an equivalent equation is to just multiply everything by a constant value. So if I multiply this whole equation by 2, for example, I would have 2y equals negative 3x plus 10. That will also create, let's put a little or there, this will also create an infinite number of solutions, a line that basically sits right on top of it. That's a dependent system. If I were to graph it, it would look like this, right on top. There's our points. This one's a little bit off, but that's what it is. There we go, and we'll draw a line through it, top to bottom, right on top of the green one. I'm missing it a little bit on purpose just so you can still see the green one a bit. There we go. We don't need to label the y-intercept, it's right there. We don't need to label the equation, but that's it. Well, you know what, we'll label it with the other one. So 2y equals negative 3x plus 10. There we go. So that is a dependent system, one that sits right on top of the other one. So we have inconsistent, no solutions, dependent, infinite solutions. The third one, and this is the majority of the cases where you would have 2 or more lines on a coordinate plane, we call that an independent system, where there's only one solution. Now this line I've drawn on here, that's just the original one that we drew on before. That's the y equals negative 3 over 2x plus 5. We are going to consider now what would result in there being only one solution if we were to draw another line on here. And the answer is we would need it to have a different slope. A different slope would result at one point somewhere in the coordinate plane, moving to infinity in all 4 directions, somewhere it would cross, just once, at one point only. The y-intercept, interestingly enough, could be the same, or it could be different. Essentially, it doesn't really matter what's happening with the y-intercepts. The reason being, if the y-intercept happens to be the place where they cross, then it'll be the same. If the place where they cross isn't the y-intercept, then they will have different y-intercepts, but it doesn't change the nature of the system itself. So let's put a second example of a possible equation in here. This can literally be anything as long as the slope isn't negative 3 halves. Now I'm going to try to create something here that is, well, we'll do it in purple. I'm going to try to do something that's actually going to go through, let's do it at -2. So let's do y equals 1 over 4x minus 2. Something that's actually going to, where the cross is actually going to happen on the graph. So I've just made that up. It literally could be anything as long as this is not -3 halves. Has to have a different slope. So we are going to start based on our slope y-intercept form at -2. There's a -2. We're going to go up 1 and over 4. 1, 2, 3, 4. We're going to go up 1 and over 1, 2, 3, 4. Let's go in the other direction. 1, 2, 3, 4. 1, 2, 3, 4. There we go. I'll try to draw a straight line through that, or something approaching a straight line. Yep, looks pretty good. All right, let's label our y-intercept. Our y-intercept is 0, -2. And our equation, I believe, was y equals 1/4 x minus 2. Oh, actually, we have a nice x-intercept as well. We should label. So that's 5, 6, 7, 8. So 0, whoops, that should be 8. 0 would be our x-intercept. And there we go. So that is the 3 ways that lines can interact on a coordinate plane. First one, inconsistent system. No solutions. The lines are parallel. They have the same slope, but different y-intercepts. Second one is a dependent system. This will have infinite solutions, and it's because it's essentially the same line. Has the same slope, has the same y-intercept. The last way they could interact is an independent system, and it has only one solution. And that means that the slopes are different and the y-intercept same or different. Doesn't really matter. The key to the independent system is that the slopes of the 2 lines must be different, and then they will have one point of intersection somewhere in space. So in order for us to utilize this information, we're going to head down onto the second page, and we are going to manipulate some linear systems to make some predictions about how many solutions they're going to have. That's in part 2 of this video, so come on back for that excitement.